Swayam Prabha. Digital India. Educated India.
Welcome to lecture 5 of week 4 on this NPTEL course on muffler acoustics. We will do things like simple expansion chamber, which is really the most fundamental muffler element that is used. So, basically, as you can now guess that a simple expansion chamber, something like this, you have your thing like this and you have and here you have something like this. So, the section can be elliptical, this section it can be elliptical or a circular thing. Shells are of circular cross section. They can also be elliptical, but circular are the ones that are more preferred because they have less breakout noise, they have more rigidity like I was mentioning. And this is the inlet port and this is the outlet port. I will call this as this point as 1 just at the interface, but within the inlet pipe, and this is the point 2 which is just in the chamber, but at the interface of the port in the chamber. This is point 3, this is point 4, inlet, outlet. Okay. So, now what is our job? And of course, I forgot to mention the length is L, the diameter, let us say the diameter is D, and let us say this dimension or diameter is D naught and this is D naught, small d naught, big D naught. Okay. So, what is our job then? To analyze a simple expansion chamber muffler. It is called simple because there is really nothing in the chamber, it is an empty chamber. It works on the principle of reflecting a significant portion or part of the acoustic energy back into the system. So, when a wave is incident somewhere in here, some part is reflected back, A1, B1, here it gets to A2 and here it is B2 and some part is A3 and here there will be some part that will be reflected back. Of course, if you have an anechoic termination, this will not be the case. So, let us assume that this is discharging into an anechoic termination. So, I will kind of rub this thing and what I am going to do is that put a anechoic termination as we discussed. So, things like this. Anechoic termination. Now, what do we do? If you recall from the last week's lecture, we wish to combine the sudden expansion plus the sudden contraction, considering the finite length effects of a chamber is no longer infinite and at least a chamber, and we are trying to determine how the transmission loss performance will be. That is to say, if a certain amount of acoustic power is incident on the muffler from here and certain amount is going towards the anechoic termination, what is the performance of the muffler look like across the frequency spectrum? To answer this question, I guess it is time that we now start talking about the field continuity conditions at the point 1 and 2 and 3 and 4 and relate it with the standing or the progressive wave variables. So, pressure at 1 is given by, we will fix the coordinate system there, E j k naught x plus this thing and mass velocity, as we probably can know by now. These formulas we should commit to our memory by y1. So, this is characteristic impedance y1, y2 and y3. So, of course, putting x is equal to 0, we get this and we get this, we get this. So, let me write it more compactly, it is B1 and this is minus B1. So, this is what we are going to get, and similar tilde V1 tilde P2, P2 is nothing but A2 plus B2 right at x is equal to 0, and this is A2 minus B2 by Y2. So, at x is equal to 0, that is to say here at this part and this is x is equal to L. P1 tilde is equal to P2 tilde, and mass velocities, if you recall, they are also the same what we derived in the last lecture. So, what do we do after this? We start putting, well, the entire idea then is to actually formulate a set of equations. Eventually, we would need everything in terms of A1. So, there will be A1, A2, A1, B1, A2, B2, A3 and B3 will be 0 if we assume anechoic termination, nothing is coming back. So, all the parameters, that is to say, let me write it down in this slide, B2, A2, B1 and your A3 will all be a function of A1. We will get this, but it will be pretty cumbersome. We can sure formulate the equations if we get things like, let me write it down first, A1 plus B1 is equal to A2 plus B2. So, this is your equation, let us say 1, and A1 minus B1 by Y1 is equal to A2 minus B2 by Y2, which is nothing but equation 2. So, we have got this equation, and then we will keep this thing aside here, and we will probably have to worry about the things that happen somewhere here at the section 3 and 4. The same field continuity conditions will apply. So, what are that? Let us figure out that part. So, here P2 tilde is equal to P3 at x is equal to L, and V2 tilde is equal to V3 tilde also at x is equal to L. So, what does it mean then? A2 into e to the power minus j k naught L. Here, now the thing is that here you will have L. Why? Because it's the pressure field is A into e to the power minus j k naught x plus B into e to the power plus j k naught x. So, the idea is that what you have to put, if you are putting your coordinate system somewhere here, x is equal to 0, here will be x is equal to L, and you will get things like this thing. So, this will happen, and then you will get, and for the other chamber you can just put it the coordinate system again translated. For this port you can define the local coordinate system somewhere here, x is equal to 0. So, you will just get e to the power 0. So, A2 and this is Y2, this is A3 by Y3. So, this is 2 3 and 4. Okay. Eventually, like I said, we want to figure out everything in terms of A1. So, we have got 4 equations, 1, 2, 1, 2, 3 and 4, and we want to find out things in terms of A1. So, it is going to be a little algebraically a bit tedious. So, I guess now it is a time to start working in terms of the transfer matrices, which will make our life very convenient. So, let us do that. You will soon see that why all these things that I am talking about is important. So, when we have this condition P1 is equal to P2, V1 is equal to V2, we can write this set of equations something like here P1 V1 is equal to 1 and 1 identity matrix, and here you have P2 and V2. Okay. You can just check by multiplying out the matrices. It's a 2 cross 2 system. Now, similarly at the other discontinuity, you have P2 V2 is equal to at x, this is of course at x is equal to 0. This is also an identity matrix at this point at x is equal to L. Okay. Now, what happens between x is equal to 0 and x is equal to L? Between the points here 2 and 3, what happens? How do you relate A2 and B2? So, right now we are in terms of the standing wave variables, that is P and V. We have not used the progressive wave variables in the matrix representation shown in this slide. We would want basically, I guess it is time now to derive also the transfer matrix for a tube with planar wave propagation, and that will really help us relate things with point 2 and 3 here. So, to that end, what we will probably do is we will probably use this set of equations as well as this set of equations, and from that we will kind of eliminate A2 and B2 to relate things at section 2 to section 3, and then we can just simply multiply the matrices. So, let us do that. Now that we have got the transfer matrix, we have written down the relation between the upstream and downstream state variables at the sudden area expansions and the contractions as we see in slide number 21 between 1 and 2 and 3 and 4. Now, what remains is to derive, basically relate the state variables between point 2 and point 3, that is pressure and velocity at point 2 with those at the point 3. So, how do we do it? Basically our objective should be to basically derive the relation, a transfer matrix relation between the pressure and velocity at the dotted section here at the interface, and I mean at this section to that at the section 3. So, how do we go about doing that? So, let us make use of this thing. So, we have here P at x is equal to L, we have this kind of a thing. Now, this should be pretty straightforward because we know from the last equations that pressure 1 is equal to pressure at the point 2 and volume velocity at the point 1 is equal to the volume velocity at point 2. So, this is straight away putting the argument of the complex exponential to be 0. So, we get this. Now, at x is equal to L, it is a matter of just actually using the length of the chamber. So, we substitute that to get A2 into e to exponential e to the power minus j k naught L plus B2 into e to the power j k naught L and so on for the acoustic pressure. So, basically we tend to use this thing for the acoustic pressure and the below expression for the volume velocity at the section 3. So, what happens now is that this is something that we are aware of, these things, and we now introduce, because to simplify the algebra, let us introduce a convention that complex exponential e to the power j is equal to cos theta plus j sin theta. So, I am calling it C plus j sin s, that is your Euler's formula. People who have some background in engineering mathematics would immediately recognize this is the Euler's formula. So, very convenient to write cosine and sine functions together. So, here we have P acoustic pressure at section x is equal to L is given by this relation. So, now we simplify, we kind of expand using the Euler formula. So, this becomes C minus Js, just substitute instead of theta, substitute minus theta and you will get this, and then B2 into C plus Js. Now, what we do is regroup the terms. So, cosine into A2 plus B2 minus j times sin k naught L into A2 minus B2. So, basically what happens is that this thing is the pressure, and we immediately recognize that this would be the velocity thing. So, what happens is pressure at the section x is equal to L is cosine times pressure at x is equal to 0 minus j sin y2 times velocity at x is equal to L. Y2 because let us recall our last relationship. From this bit we get y2 into v of x naught, v velocity, volume velocity within the chamber at x is equal to 0. So, in place of that we are using this thing here, and we are using this part here. So, once we do that, we immediately recognize that P acoustic pressure within the chamber right at x is equal to L section is cosine times the acoustic pressure at x is equal to 0 within the chamber, that is at the other end, minus j into sine k naught L times y 2 into V of x is equal to 0. Now, volume velocity similarly can be expressed as 1 by y 2 times a 2 into complex exponential minus b 2 times another complex exponential. As usual, we go about multiplying, just to simplify terms, we multiply both sides by y 2 and expand the Euler formula, expand these terms using Euler formula, and once we do that, we will rearrange the terms a 2 into j times sine k naught L, similarly for the terms underlined here, and then we regroup the terms a 2 minus b 2 minus j sine k naught L a 2 plus b 2, and this is nothing but your pressure at x is equal to 0, and this is nothing but velocity at x is equal to 0. So, we get another relation, this one and this one. So, now we can clearly very easily write that in the matrix form, but hang on, just before that what we will probably do is obviously divide both sides by y 2, and so in the end we will get something like volume velocity at x is equal to L is equal to cosine times volume velocity at x is equal to 0 minus j sine k naught L divided by y 2 into acoustic pressure at x is equal to 0, where obviously y 2 is your characteristic impedance of the chamber, which is given by C naught times the cross sectional area of the chamber. So, when you write this entire thing in a compact nice 2 by 2 matrix form, what are we going to get? We are going to get a 2 cross 2 matrix, pressure, but hang on, we are able to relate in a matrix form pressure at the section x is equal to L with the pressure and volume velocity at x is equal to 0. That is, this is the D downstream variable, this is the upstream variable. So, once we do that, what we are going to get is basically relation between this point and this point, okay, this point and this point. So, now what we would transfer matrix means something like, if you recall our last lectures, we would be trying to relate the upstream variable to the downstream variable, that is the variables at the point x is equal to 2 or 0.2 or x is equal to 0 to the variables at x is equal to L. Right now it is just the inverse. So, let us focus on how do we go about doing that. We just need to, the idea is fairly simple, we just need to take the matrix inverse, that is, let us say this is the matrix say T1. So, if you just invert the matrix, that is T is equal to T1 inverse, matrix T is matrix T1 inverse. So, we will get this form. We can actually multiply this matrix, the one underlined, with the matrix somewhere here, and you see that we will get an identity matrix. It is fairly simple to see. So, I am not going to derive it here, this is left as an exercise for the students here. Basically, the idea is that try to invert this matrix. So, when you invert this matrix, whatever matrix you are getting is shown here. Now, the upstream variables and downstream variables are related by a nice clean transfer matrix, which is your this thing. So, this is nothing but, let me simplify things for you or make it more clear. This is cos, so is this, and your j into sine of k naught L by y 2, j into sine of k naught L by y 2. So, well, we have our 2 cross 2 matrix which relates upstream variables to the downstream variables. So, we will see this is probably one of the very important fundamental results in Muffler acoustics, and we probably had to wait till the last lecture of week 4 to arrive at this, but this was all kind of building momentum, building enough background to arrive at this fundamental result. So, you can pause the screen, reflect and have a look at this transfer matrix in a perhaps in a more with a much more attention. There are lots of properties what can be revealed just by looking at this, like I will probably not be discussing all those things, but probably something about conservative system, reciprocal systems and symmetric systems, and those details are there. Lot of things can be done. Determinant, one couple of things that I would like to point out. Determinant of such a transfer matrix is always unity, that is determinant of T is unity. Read more about what does it mean in terms of energy conservation or reciprocity of the stuff. So, since there is one more thing that because the element is really symmetric, we have a uniform tube like this, we are relating 1 to 2 or whatever terminology we are using. So, if we were to invert the matrix like we have seen here, apart from the difference in the minus sign, everything else is the same, and actually by changing the sign conventions of mass velocity, we can actually see that the inverse would be the same as the T matrix. So, that is characteristic of the fact that this is a uniform tube. So, if you even if you reverse the element, the transfer matrix would be the same. Probably later in the course we will come up with a thing like impedance matrix, not now, but later on when we are dealing with a network analysis, and then again try to correlate this. But for now, let us bread and butter would be the transfer matrix. Now that we have derived the transfer matrix for uniform tube, now this is valid whether it is a chamber of diameter capital D naught, big diameter, or a small diameter, as long as plane wave propagation is there. So, this transfer matrix is there. So, what is the limit? If you recall the lectures from week 2, what for a duct of radius r naught or diameter d naught, the cut on frequency for the 1-0 mode, 1-0, you know, if you recall our discussion, this was the plane wave mode, this was the first circumferential mode and so on, and this was the first radial mode, second radial mode and so on. So, like this there will be a cross mode, plus minus, minus plus and so on. So, we are talking here about the cut on frequency of this mode, that is the lowest first higher order mode to propagate. This is the planar wave mode, always propagates for a rigid duct. This is the cut on frequency of the first higher order mode, also known as the 1-0 mode. 1-0 mode. Recall the lectures from week 2. The reason that I am telling you is this, because if the frequency is such that 2 pi f by c naught is equal to 1.84, let us make it simple, r naught. So, f is c naught by pi and 2 r naught is d naught times 1.84, 12 well. So, f c is c naught by d naught and 1.8412 divided by pi. Let us quickly work out what is it going to be. So, I guess we discussed this briefly, but it is probably worthwhile to mention this thing again here. It's probably f c is 0.5861 times c naught by d naught. So, the point I am trying to make is that this transfer matrix is a valid one if you are well within or probably less than the frequency given by this thing, because at such frequencies only the planar waves will propagate. So, this cut on frequency obviously will change for an elliptical duct, something that we again discussed long time back, and for a rectangular duct it will be a different expression. But so, the idea is find out the propagation frequencies of the lowest order mode and then check if you are above or below that frequency. If you are below, then the transfer matrix for a uniform tube will apply. Now, quickly getting back to our, I guess we digressed quite a bit, but that was important. We will use this thing, this matrix here, along with what we saw probably in the slide here, and gradually kind of multiply. So, the thing is that we can comfortably now see that if you are considering the muffler system like what we discussed in slide number this one. So, we know relation between 1 and 2, 2 and 3 was just derived, the transfer matrix, 3 and 4 we know. So, we can relate what happens to 1 and 4. Okay. So, once we do that, we can just say P1 times volume velocity V1 is equal to identity matrix times P2 tilde V2 tilde and P2 tilde V2 is equal to that familiar C j sin y, j sin by y cos and P 3 times V 3 and 3 and 4 are something that we know of. So, we all know that. So, I is the identity matrix 1 0, diagonal elements being 1 0 as we know. So, 2 cross 2 stuff. So, now it is just a matter of sequentially multiplying the elements. So, let me write it down like this P1. So, identity matrix times this thing is just this matrix, and again this matrix times identity matrix just the cos k naught L j sin y k naught L into your y 2, and this is j by y 2 times sin k naught L, and this is your cos k naught L. So, P 4 and V 4. So, we get finally when we have such a muffler. So, pay attention to the fact that the point 1 is just in this pipe outside the chamber and point 4 is just outside the chamber in the outlet pipe. So, we know all those things, and now what do? We would basically want to further relate the incident wave variables at the inlet port to the thing that was transmitted. Remember, we have an anechoic termination. So, we know it is A1 here and we know it is A4 here, or what was it? I guess it was probably, let me just recall, was it A3 or just the point was 4. So, P4, but it is A3, the point obviously is 4, but it is A3. So, what we would probably be doing is that, let me just go back and verify my algebraic simplifications, and now what we would probably be doing is that P1 is equal to A1 plus B1 and V1 into Y, let us call this as Y1. Let us assume the diameter of inlet and outlet ports are the same. So, Y1 is equal to Y3 is equal to A1 minus B1 and B3 is 0. So, P4 is just A3 and V4 into Y3 is just A3. So, we will put those things in here and proceed further. So, A1 minus B1 by Y1, this is what we are going to get, C j sin y, j sin by y cos A3 by Y3. This is what we are going to get, assuming anechoic termination, of course. Now, things should be relatively much more simple. So, A1 plus B1, let us expand this thing, let us consider the first equation of the matrix thing. So, this is A into A3 plus j sin Y2 into A3 by Y3, and A1 minus B1 is equal to j sin by Y2 into Y1 into A3 plus C times Y, and Y3 of course is, like I said, Y1. So, A3 into Y1 this will cancel, and so I will rather not write this term and just bother with writing A3. Okay. So, now I guess you guys should be able to figure out just adding these two equations, that is your equation star and double star. So, if we add these two equations, what will we get? 2A1 is equal to, we will take A3 common throughout. So, let me write this A3 somewhere here, assuming that we will need that much space. So, C, so what will we get? C, or rather cos k naught L, and we will get contribution from cos k naught again here. So, I would write this as 2 times cos of k naught L, okay, and j sin y, and this of course is 1. So, I would write this as j sin k naught L times y2 by y1 and plus j sin k naught L into y1 by y2, because that is what this is here, and this would probably simplify. So, A1, so the ratio of A1 by A3 is nothing but this would be cos of k naught L and plus half times j sin k naught L times y2 by y1 plus y1 by y2 and this thing. So, we get this form. Now, let us see what happens after this. We need to worry about that as well. We need to worry about that. Now, transmission loss, if you recall, was defined as 20 log 10 by A1 incident wave by transmitted wave, isn't it? Or it was just 10 times square, whatever whatever form is convenient to you. Right now, it is something like mod of this entire thing, cos of k naught L times plus j by sin k naught L times 2. And so, now let us assume that y2 is nothing but C naught by S2 and y1 is nothing but C naught by S1. So, it is y2 by y1 is S1 by S2. So, remember S1 is smaller, is the port, and S2 is bigger. So, let me call this as 1 by m, and obviously y1 by y2 would become m, where m is, if you recall, square of the diameter of the chamber to the port. So, m is equal to d by d naught square. So, it will be pretty much convenient to write it like this. So, then it will be y2 by y1, we just derive, it is 1 by m plus m. So, 1 by m plus m, we get this, and it will be like this. So, we could possibly simplify the terms and probably worry about that. So, let us do the simplification. Now, we need to simplify this thing. So, we immediately recognize that, like, well, this is of the form z is equal to a plus j times b. So, what is the magnitude of z is equal to a plus jb? It is root over z, mod of z is a square plus b square. Let me just rub it because of clarity space. So, this is your one term, real term, a square cos square k naught L plus sin square k naught L by 4 into m plus 1 by m whole square. Okay. So, that is what we are going to get. Now, they are clearly the form a square plus b square. Now, it is a simple, fairly straightforward algebraic trigonometric simplification. It is one we express cos in terms of sine, and rearrange the term sin k naught square L is taken common, this term is there, and so what we do basically expand this thing out, m square plus 1 by m square, 1 by 4th factor is always there, and 1 by 4 into 2 by 4 and minus m is there. So, what happens is now is that this is further simplified, half minus 1, that is minus half. So, once you multiply this by 2 and 2, so what we get is basically 4. So, 2 times 4. So, we will take sines square k naught L by 4 common, and m square plus 1 by m square minus 2 m into 1 by m. We take this thing. So, we get the following, m minus 1 by m whole square, we get this. So, then the transmission loss can be written very conveniently in terms of the following expression. It is 10 times log 10. Remember 20, it is not 20, it is 10, because we have taken this thing here square. So, let us discuss very briefly about the consequences of such a thing. So, this is the finally the much coveted expression that we aimed for at the beginning of this lecture 5 of week 4. It is a nice, beautiful, compact relationship, and probably we will worry about the consequences of or probably the implications of this relation in the next lecture, that is week 5 lecture 1. It is a fairly detailed, we can probably like to do a fairly detailed analysis of how the transmission loss varies with frequency for a simple expansion chamber. So, basically just as a teaser for a result, just to keep your curiosity alive. So, if this is the frequency axis or non-dimensional frequency axis, non-dimensional with respect to the length L, k naught L, and this is your transmission loss. So, you will get domes at frequency attenuation domes, and how does this vary with m, that is the expansion chamber ratio, and what are the frequencies at which your crest or the maximum or the transmission loss happens, and where does your trough happens. We will see all this later. Stay tuned, thanks a lot.